For years, the default method for saving machine learning models relied on Python's legacy Pickle module. This involved taking massive files of neural network weights and loading them directly into privileged production environments. The Pickle format was designed for high flexibility, allowing developers to serialize arbitrary Python object states along with their specific internal behaviors. To reconstruct these objects during loading, Pickle utilizes a stack-based virtual machine that is embedded directly into the .pt or .bin model files. This architecture introduces a vulnerability known as remote code execution, or RCE. RCE is a security flaw that allows an attacker to execute arbitrary commands on a target machine or network. An attacker can exploit this by overriding a Python class's __reduce __ method, which returns a tuple containing system-level commands. This code layout illustrates the risk. On the left, the server executes a standard torch.load command. On the right, that same command simultaneously triggers a hidden reverse shell initialization. The malicious payload executes the moment the weights are loaded. In 2024 and 2025, security researchers at JFrog identified thousands of functionally valid Hugging Face models carrying these hidden payloads, a period of widespread exploitation known as the Sleepy Pickle Era. The industry had prioritized developer convenience and the ability to save complex object states over the security of the underlying infrastructure. Traditional security scanners were often unable to detect these vulnerabilities. Because the execution occurs dynamically within the Pickle virtual machine layer, the malicious logic remains hidden from static analysis. Alternatives like the Open Neural Network Exchange, or ONNX, faced similar hurdles. ONNX is an open format designed to allow machine learning models to be moved between different frameworks. However, ONNX serializes the executable computational graph, which can still be targeted during runtime graph compilation. In late 2022, Hugging Face engineers began developing Safetensors with the goal of creating a strictly dumb serialization format. The design required the removal of all executable logic, architectural graphs, and optimizer states, leaving only raw numerical data. This forces developers to define the model architecture in transparent, separate codebases, rather than hiding the logic inside the weights file. By isolating the weights from the execution path, the deserialization engine treats the file as inert data. This structural guarantee prevents the parser from ever misinterpreting a mathematical parameter as a system command. Safetensors operates on a principle of extreme structural constraint. It enforces a rigid separation between the file's metadata and the raw parameter data. This diagram shows the three-layer layout of a Safetensors file. The strict 8-byte prefix declares exactly the byte size of the subsequent JSON header, removing any ambiguity about where the data buffer starts. The JSON header expands, mapping tensor names to their exact data offsets, capped at 100 megabytes. It points directly to the third segment, a contiguous, uncompressed byte buffer packed with no internal gaps or anomalous padding. The data offsets in the JSON header specify byte ranges relative to the start of this buffer, rather than the absolute beginning of the file. By forcing data into this uncompressed array, Safetensors neutralize the risk of code injection and enabled high-performance operating system primitives. This diagram illustrates the sequential I/O pipeline used by legacy formats. Data moves through the kernel cache and user space RAM before reaching the GPU, requiring multiple memory allocations and frequently doubling the host RAM required. Safetensors avoids this by using memory mapping, an operating system feature that maps a file's content directly into a process's virtual memory space, bypassing the user space RAM entirely. Because the weights are stored contiguously without compression, the operating system can page required byte ranges directly into memory as needed. Tensor objects are instantiated as pointers to these mapped memory addresses. The data is never copied into the host RAM, achieving true zero-copy loading. This layout natively supports distributed partial loading. A node in a compute cluster parses the JSON header, mapping only the specific slices, like attention layers, needed for a specific task. Eliminating the executable logic within the file directly enabled the use of memory mapping, which resolved the primary I/O bottleneck facing large-scale inference. Even with memory mapping, sequentially initializing massive models still consumed significant host CPU resources. In 2025, researchers at IBM introduced Fast Safetensors to solve this. This hardware view shows the loading flow redesigned to decouple file I/O from tensor instantiation. Utilizing GPU direct storage and direct memory access, data blocks stream from the drive straight to the VRAM, entirely bypassing the CPU. Once the raw bytes are in the video RAM, the tensors are instantly formed in place using the DL-Pack memory standard. DL-Pack is an open-source memory structure that allows different machine learning frameworks to share tensor data without performing a copy. The framework calculates memory layout strides based on data type and tensor shape, ensuring the raw data blocks instantly snap into structured, multidimensional grids. This direct streaming method accelerated loading for the 176 billion parameter Bloom model by 4.8 to 7.5 times compared to standard Safetensors loading. The contiguous layout of Safetensors provided the specific structural requirements needed to leverage the physical limits of hardware-level direct memory access. It is a common misconception that the .safetensors file extension somehow indicates the underlying model is mathematically benign. Safetensors secures the infrastructure by neutralizing the file parser, but it has no visibility into the actual mathematical values of the weights. This limitation allows for data poisoning, where an attacker distributes valid tensors that have been mathematically optimized to output malicious code or bypass safety guardrails. This sequence represents an FP16 floating point weight, a 16-bit format balancing precision and memory. Here we see Tensor Steganography. Attackers encode ransomware binaries into these least significant bits. To the Safetensors metadata header, the file appears perfectly valid. Loading the file will not execute the code, but it transforms the model into an undetectable courier for moving large payloads across secure corporate networks. Safetensors secured the loading mechanism itself, but this success shifted the security focus toward the deep statistical analysis of the weights. These security guarantees are central to the 2026 landscape of Agentic AI, where enterprise systems deploy autonomous models. As models gain the autonomy to manage workflows and cloud infrastructure, a compromised model load can result in total infrastructure failure. The deterministic zero-code execution environment of Safetensors provides a necessary foundation for these autonomous deployments. Before an agent is granted operational agency, its parameters must be loaded into clusters with absolute certainty that no code execution vector exists. The machine learning serialization crisis highlights a fundamental, unyielding rule in the modern design of secure software protocols. Prior attempts to maximize developer flexibility through complex serialization actively undermined the trust boundaries required for execution. Safetensors succeeded by demonstrating that high computational performance and system security are achieved through aggressive, uncompromising inflexibility.